Hi, this video is about solids. It's just about the different types of solids and some of their physical properties. So in this video, we're going to talk about metallic solids, ionic solids, covalent network solids, and molecular solids. All right, before we start talking about metallic solids, I thought we should review metallic bonding. Metallic bonding is described as having delocalized electrons, or a sea of electrons. So these valence electrons, they're not associated with any one atom. They're just kind of free floating and around an array of positively charged metal cores. And so whenever you think of metallic bonding, think of sea of electrons, or electrons that just aren't located in one spot. They don't belong to just one atom. So you've got these positively charged metal cores with these mobile valence electrons. And this is kind of a picture trying to show that. So you've got the positive metal ion, silver +1, and then those clouds, or the valence electrons, are just kind of free floating and delocalized. All right, so these delocalized electrons, thinking about the physical properties of metals, the delocalized electrons explains a lot. First of all, metals, we know, are good conductors of electricity. And so that's because of here is Zeus again. He always photobombs us. That is because of the sea of electrons. Also, metals are malleable and they're ductile and they have low volatility. And all of these physical properties of metals are due to the delocalized electrons. All right, well, let's talk about metallic solids. So a metallic solid can be just one pure metal, or it can be a mixture of metals or other things. And when a metal is in a mixture, it's called an alloy. Now, an alloy, even though it is a mixture, is going to retain the sea of electron metallic bonding. And like surfaces of alloys can change due to chemical reactions. You can just think of, something rusting or reacting with oxygen. All right, well, there are two types of alloys, and one of them is called the interstitial alloy, and that's when you have a metal atom and then something else, another atom that has a different radius. So two different sized atoms, and the smaller atoms are going to fill in the interstitial spaces of the larger atoms, or spaces between the larger atoms. And a good example of this is stainless steel, which you've got the larger iron atoms and then carbon kind of tucked in there. Now, what happens when we've got these smaller atoms tucked in these interstitial spaces of the larger atoms, the metallic lattice becomes more rigid, and the alloy is now less malleable and it's less ductile. So I like to think of when you're alloying a metal, you're making it stronger. The other type of an alloy is substitutional alloys, and that's where you just substitute in another metal. They're pretty much comparable sizes. So for instance, brass is an alloy of copper and zinc, and copper and zinc, they're both in that 3D portion of the periodic table, and they're pretty comparable in size. And so that's just when one atom substitutes in for another atom in the lattice, but they have similar sizes. Now, the density would be somewhere between the copper and the zinc, so brass's density would be somewhere in between theirs. And again, because of this alloy, these metals now, the metal alloy, they're less malleable and less ductile than the pure metal by themselves. All right, so now let's talk about another kind of solid, and it's called an ionic solid. It's made from a metal and a non-metal, and they have high melting points. They only conduct a current, and we say when something conducts a current, we call them an electrolyte, if they are melted, and we call that molten, or when they're dissolved in solution. If it's just a solid ionic compound, it will not conduct electricity. And they are also brittle. So let's talk about these physical properties. Ionic solids generally have a low vapor pressure, because in an ionic solid, we got to think about Coulomb's law again. We've got these positive and negative ions, and they're arranged in a regular three-dimensional array. And remember, the larger the charge, so the force of attraction between these, or the force of repulsion, but it's going to be the force of attraction in this ionic solid, is proportional to the magnitude of the charge on the on the ion, and it's inversely proportional to the square of the radius. So anyway, they have this Coulombic attraction, and ionic solids tend to be brittle because of the repulsion of like charges caused when one layer is on top of another layer. So that causes them to be brittle. Now, these ionic solids, like I said, when they're in the solid form, they do not conduct electricity. But if you melted it and then you would say it was molten, then you are freeing up these ions to move, and they do conduct electricity. Or if you were to dissolve them, if it was something that dissolved in water, it would then conduct electricity. So an aqueous ionic solution would also be an electrolyte. Okay, so again, we just talked about when these ionic solids dissolve in water, they're separated into the free, and the ions are free to move, and that is why they are conducting electricity. When something dissolves in water, that the positive portion on the hydrogen is going to pull on the negative ion, and the partial negative charge on the oxygen from water will pull on the positive ion, and it will break up the crystal lattice, and then you've got ions in solution, which conducts electricity. Ionic compounds don't tend to dissolve in nonpolar solvents. So like water is very polar, that's separation of charge, but in nonpolar solvents, they don't tend to dissolve because the attraction among the ions in the ionic solid are stronger than the attractions for the nonpolar solvent. All right, melting points of ionic solids tend to be high. And the reason is again, we're trying to separate opposite charges. And so if you've got smaller ions, so the distance between the ion centers is smaller, that's going to make the force, if you look at Coulomb's law, that's going to make the force needed to separate them stronger, and they're going to have a higher melting point. So if we have a smaller distance between ion centers, it's going to have a higher melting point. Now, if ions have a larger charge, now remember Coulomb's law, remember the force is proportional to the magnitude of the charge. So if you had like a +2 ion compared to a +1 ion, the +2 ion would have like the higher melting point. All right, covalent network solids is the next one we want to talk about. And this is just a very select few solids. They are atoms that are covalently bonded. I like to think of their intermolecular forces as covalent bonds. I don't really know if that's the right way to describe it or not, but they are covalently bonded into a 2 or a 3-dimensional network. So they have they're extremely hard, and they have extremely high melting points. So compared to, say, even an ionic solid whose melting point is high, covalent network solids tend to have the higher melting point, and they tend to be extremely hard as well. So how do we identify a covalent network solid? Well, there's not many of them. They're only formed from nonmetals. So like, for instance, elemental carbon, like diamond or graphite. So normally when you have a phase change, if something goes from like a solid to a liquid, you are breaking intermolecular forces. But if you were going to melt diamond or graphite, you are actually having to break covalent bonds that are holding those carbon atoms together. And that is why the melting point is so high for these things. Also, covalent network solids can be 2 nonmetals, like silicon dioxide or silicon carbide. Just to remind you, silicon is a very important element and is a semiconductor in electronics. Okay, so why do they have such high melting points? It's because all the atoms are covalently bonded together, and a covalent bond is much, much stronger than intermolecular forces, even stronger than definitely hydrogen bonds or dipole-dipole forces. These covalent bonds are strong, and you'd have to break them. All right, they're hard and rigid because covalent network solids tend to have these covalent bonds where the angles are fixed, so they're hard and rigid. All right, so the covalent, whenever you see like silicon or quartz, diamond, graphite, those are covalent network solids, and they have high melting points. When you melt them, if they go from a solid to a liquid, you are actually breaking covalent bonds. You are not just breaking intermolecular forces. Okay, now molecular solids consist of all nonmetals, so our diatomic elements like iodine, and or compounds that are formed between two or more nonmetals. And physical properties are almost just the opposite of ionic. They don't conduct electricity. Their electrons are tightly held in covalent bonds, so they don't ionize. They have low melting points because they have relatively weak intermolecular forces, unlike, those covalent network solids where they're held together by covalent bonds. Now, molecular solids can be some very large molecules sometimes, so their dispersion forces can get pretty large because their electron clouds can get pretty large, but they're called polymers, and they're important in commercial and biological applications. But again, they don't conduct electricity. They have relatively low melting points and so forth. Okay, well, we're going to practice some questions about these different types of solids, and have a good evening.